just need to sum up, sorry. I just need to sum up, so I'm going to sum up. So we're doing salt solutions. We've been talking about an ionic compound. Ionic, meaning that it dissociates completely into ions, and so therefore it's a good electrolyte. And an electrolyte is a solution which conducts electricity. And now we're talking about basically defining an acid and a base. An acid, like HCl, is going to give off a hydrogen ion, and then you're going to have your base, which is Cl minus, remaining. You can take H2SO4, which also will lose an H+, and that will leave us with HSO4-, and I apologize, I didn't finish this thought over here. A polyprotic acid has more than one H+ to donate. Because remember, we're working with the Bronsted-Lowry definition. So an acid donates protons and a base accepts protons. So the interesting thing about this HSO4- is that it is called amphiprotic. So just like an amphibian, which can live on land and water, amphiprotic can be an acid or a base. Hydrogen sulfate can either accept a proton and act as a base, leading it back to sulfuric acid, or it can lose a proton and become an acid, acting as an acid and go back to sulfate. So it is amphiprotic, and they can act as both acid and base, acid or base. Water is also amphiprotic, depending on what water is with, and I think we talked about this before. It can either lose a proton, becoming OH-, or it can gain a proton, becoming H3O+. Okay, so that's also amphiprotic. Now, it's important to note that H2SO4, just as a little side note, H2SO4 is a strong acid, while HSO4- as an acid is a very weak acid. So really, when you put H2SO4 into water, the acids mostly come from that first monoprotic removal. Okay, we also could look at hydrofluoric acid, which is also going to lose a hydrogen, and it will become fluoride. So if we look at bases, then a good base to look at is ammonia, which is a weak base, and ammonia is going to accept a proton. And when it does, it's going to come to this conjugate acid, right, of NH4+. So in this case, this is going to act as a base. Ammonium will act as the conjugate acid. So salts are made of ions, so they can either be basic here, the ion, or they can be acidic here, right? And the way we figure this out is because we know that the Ka, for example, the Ka of HF times the Kb of F- is equal to Kw. Kw is 1.0 times 10 to the minus 14 at 25 degrees Celsius. We also know that the stronger the acid, the weaker the base. The weaker the conjugate base. And we can see this because if we look at this equation with Kw being a constant, as we increase the Ka, the Kb must decrease. So the stronger the acid, the weaker the conjugate base. And a weak acid, somewhere around 10 to the minus 7, is going to have a weak conjugate base somewhere around 10 to the minus 7. So if they're close, they're going to be similar in strength, okay? And therefore, also, the conjugate of this is true, right? The stronger the base, the weaker the acid. Okay, so the question is, if we put a salt into water, how do we know whether that solution will become acidic, basic, or neutral? Because remember, that salt is going to break up into ions. So if it breaks up into Cl minus ion, will that make it be acidic? If it breaks up into the F minus ion, will that make it be, will the F minus ion make, like if it's Kf, is that going to make the solution basic because this is a conjugate base of this acid? Or is it only the H plus that actually counts? So let's take a look at a couple examples, and I'm going to give you the format that you're going to want to use on the free response questions, all right? So the free response question is, they're going to give you a molarity, and they're going to give you everything else, but all we really care about is if we put NaCl into water, will the solution be acidic, basic, or neutral? So what we're going to do is we're going to separate our ions. So we're going to separate them into sodium. And then we're going to separate it into chlorine. And then we're going to draw a little chart. And at the top of the first box, we're going to write acidic, question mark, acid, or base with a question mark. All right, here we go. So the first one is sodium, is the sodium ion going to cause this solution to become acidic? So what we know is that the Bronsted-Lowry definition is that an acid donates protons. So can this sodium donate protons? No. It is not going to donate protons. The reason is there are no H plus ions to donate. And you can see that. There are no H plus ions there. See that? No H plus ions. So it is not going to cause this solution to be acidic. Will it cause it to be a base? Well, if we put it in water and it pulls that hydrogen ion off, right, then it will allow that solution to be basic, because remember, part of this is also about the H2O, and then the hydrogen comes off, leaving the hydroxide. So if what we're looking at pulls off the hydrogen and leaves the hydroxide, then yes, it will make the solution basic, right? Is that going to happen here? No, it is not. Why not? Because positive ions do not attract H+. So therefore, no change. There will be no change at all in the pH of this solution due to this sodium ions floating around. Questions on this? Okay, next. Cl-. Are there hydrogen ions? Nope, there are not. So can it donate hydrogen ions? No. So the answer is nope, it will not make it acidic. No hydrogen ions to donate. Okay, next, base. So can this accept protons? Because that's the definition of, a Bronsted-Lowry base. Can this ion accept protons? Yes, it can. So yes. Yes, it can accept protons. Okay. It is, and now we're going to talk about it a little bit, it is the conjugate base of HCl, right? Notice what I'm doing when I'm doing this in the free response section. I'm giving them all the information they need to know, which is justify your reasoning behind whether it's an acidic or a neutral or basic solution. Okay, it is the conjugate base of the HCl, which is a strong acid. Okay, so therefore, Cl- is too weak to affect change in pH, to change pH, right? It's too weak. All right, but here's the thing. So let's say, like, that doesn't make sense and you want more. So let's do more. So the Kb of Cl- is equal to the Kw over the HCl Ka. Everybody okay with that? So the base, the Kb of the base, is equal to the Kw over the Ka of the acid. Now, what do we know about the Ka of the acid? It is large, very large, because it's such a strong acid. So what this actually is that 1.0 times 10 to the minus 1/4 over large. So what this means is that the Kb is extremely small. So the Kb is smaller than the Kw, which is 10 to the minus 14. And so therefore, the water actually, just the water alone, produces more hydroxide than the Cl- when it pulls off those hydrogens. Because the water has a higher hydroxide content than the Kb is going to have. Yeah.
So is Cl weak because HCl is a strong acid?
Yes. So Cl is weak because if you were looking at this, you would see HCl, which has a 100%, it's so strong, it's all going to shift over. So to H plus Cl minus. Anytime that Cl minus tries to grab this and get back over here, it gets shoved back over. It cannot get back over there. It gets kicked back over. And that's why Cl is such a weak base, because it can't form HCl, because HCl can't stay formed. So it'll break apart again. All right? So that means that this is actually neutral, because the conjugate base of a strong acid does nothing. All right? And so if you want to and you understand this and you want to put this in, go ahead. But you do not. This is perfectly acceptable, because if you understand, and I'm telling you that strong acid list, if you understand that if you can say like the Cl minus as a conjugate base of that strong acid is too weak to affect the pH change, that's good enough. This is a 5-point answer, okay? So ultimately, a neutral and a neutral gives you a neutral. No change. Okay. So, we talked about, I'm just double checking to make sure I included everything. We talked about that to be a Bronsted-Lowry acid, you're going to donate the hydrogens. To be a Bronsted-Lowry base, you have to be able to accept the hydrogens. And then the stronger the acid, the weaker the conjugate base, and that this is always true. Oh, this here is always true for a strong acid, weak conjugate base. So you can always use that as your reasoning for strong acid, weak conjugate base, that the conjugate base is too weak. All right, let's go on to the next one. Let's use ammonium nitrate. And we're going to go a little bit faster, all right? So I have NH4, NO3. So the first thing I'm going to do is break it up into my ions. NH4 plus and NO3 minus. I'm going to draw my boxes. And I'm going to say, is this one an acid? And is this one a base? Now remember the criteria. Bronsted-Lowry acids have hydrogens to donate, and Bronsted-Lowry bases are proton acceptors. So NH4 plus, is it an acid? Does it have hydrogens to donate? Yes, it does. It is the conjugate acid of what? NH3. Yes, and NH3, is it strong or weak base? It's a weak base, all right? It's a weak base. So you can even put this in, weak base, all right? Okay. Is it a base? Will it accept protons? No, it will not. So no, it will not accept protons. Because it is positive. Positive, and positive does not attract. Okay, so now my summary here is, what has this done to the solution? It has made it acidic. How acidic? We're not worried about it right this minute. Because if it's acidic and neutral, then we're good to go, right? Acidic and acidic, we're good to go, okay. So next, NO3. Does it have protons to donate? No, this is not acidic. No, no protons to donate. Super simple. Is it a base? Yes. Can definitely accept, right? It can accept protons. Everybody okay with that? Now I need to describe it. What kind of an acid is nitric acid? It is the conjugate acid, a base, base of HNO3. Strong acid, weak acid? It is a strong acid.
Oh, yeah.
Okay. So what do we know? Therefore, too weak. Too weak to change pH, right? Starting to make a little bit of sense? Yeah? Okay. All right. So this is going to be, what's my result? Neutral. Oh, so basic. Oh, no, neutral. Sorry, I saw the S and I was like, no, neutral. Okay. So now when I go to write what this is going to be, NH4, NO3 solution is going to be what? Acidic. Okay? I hope you're starting to realize how important those strong acids, knowing those strong acids and bases are. Gotta know them. Okay. Next, we'll try one that we are a little less familiar with, if that's possible at this point. All right. Okay, we're going to do methylamine, CH3, NH3, NO2. Okay, so we have to split this up into, you're on your AP exam. This is the ion. How are you going to split this up? You only get two. You only get two. What are the two? What do you recognize right away that could be peeled off? What do you recognize? Yep. Okay. We recognize NH3. Good. What else do we recognize? NO2. Excellent. Good. Yes. In fact, that is correct. So the division is right here. That is where the division is. One side is positive, the other side is negative. Okay? There's no extra H added on. It's not NH4 plus, it's NH3 plus. Okay? So I'm going to split this up. CH3, NH3 plus, and then NO2 minus. Okay, so this one's going to be a little bit more complicated because I can tell you right away, one of these is a weak acid and the other one is a weak base. Okay, so acid, base. All right, here we go. So does this have hydrogens to donate? Yes, it does. It is the conjugate acid of CH3 NH2, right? When it adds a hydrogen on top of that, it becomes NH3. Now, you wouldn't know this, but this methyl group, right? This is a weak base. They would probably need to give you some numbers, but this methyl, it's called methylamine. Methylamine. If it has methyl groups in it, you can assume pretty much that it's weak, base or acid. All right, because it's got those covalent bonds that are going to buffer. All right, so you can assume that it's weak. If you don't know, assume it's weak. All right. They may give you the KB and the KA though, so then you should look around for that a bit. Okay. Next, base, can it accept protons? No, it already has a positive. So the answer is no. Positive cannot attract H plus ions. Okay, so what does that mean this is going to be? Acidic. Next, the NO2, is it going to be an acid? No. Why? No protons to donate. Okay, next, yes, it is the conjugate base of HNO2. Now, is HNO2 a weak base or a strong base? So that's a weak base. Okay. Now, that means that this is a base. So you might think that this is going to neutralize, but it's not. All right, it's not going to neutralize. The highest Ka or Kb, higher Ka or Kb will dictate acid or base. So if the Kb is higher, then it's going to be basic. If the Ka is higher, then it's going to be acidic. Okay? That makes sense, right? Because whichever one is higher, that's the one that's headed over more strongly in that direction. So in this problem, you are given the Ka of CH3, NH3, sorry, NH2. You're given the Kb, my apologies, you're given the Kb of that, which is equal to 4.4 times 10 to the minus 4. And you're given the Ka of HNO2. That makes a lot of sense, right? Okay, so you're getting the acid and then the base, right? And this is equal to 4.0 times 10 to the minus 4, which is dangerously close. That's not good that they're so close, because we're trying to determine which one is going to be bigger in the end, right? All right, so what we're going to do is we're going to find, since I know the Ka, the Kb here, I'm going to find the Ka of the conjugate acid.
I have a quick question.
Yep.
For the base of NO2 minus, is the base of HNO2, that's a weak base?
Mm-hmm.
Okay.
This is a weak base because it's got a weak acid. So remember, Ka times Kb is equal to, right? So this is 10 to the minus 4. So the other...
But down there in the chart, it says it's a weak base. Is that...
Yes, it's a weak base, conjugate base of a weak acid. This is not HNO3, it's HNO2.
No, but it's a conjugate base of a weak base.
Nope, nope, nope. I even have weak base in my notes, so I didn't have it wrong in my notes. All right. Okay, so now what we're going to do is we're going to find the Ka for CH3 NH3 plus. And we need that Ka, which is going to be equal to Kw over CH3 NH2 Kb. All right. So that's going to give us 1.0 times 10 to the minus 1/4 over, I go back up to my Kb, 4.4 times 10 to the minus 4. And that gives me 2.3 times 10 to the minus 11. Next, I'm going to find the Kb for my NO2 minus. So I'm going to take my NO2 minus, I'm going to look for my Kb, which is my Kw, over my Ka of HNO3. So that is equal to 1.0 times 10 to the minus 14 over 4.0 times 10 to the minus 4. And that is equal to 2.5 times 10 to the minus 11. Now, the problem here is that we're looking for which one is higher. And to be quite honestly, statistically, at 10 to the minus 11, 2.5 and 2.3, they are essentially the same. If they were even one apart, you could say the solution was slightly basic or slightly acid. If they were 3 exponents apart, you could say it is acidic. But in this case, the proper answer, just so we're clear, the proper answer is that the Kb and Ka are so close that the solution is neutral. All right, even though one is higher. And again, the higher the Ka or the Kb is going to dictate the acidic or the base in the solution. Okay? So, questions? Or do you want me to recap? Okay, let me recap. So what you're going to do is you're going to take, you can even label them as now this is going to be acid or base, or was acid and base, whatever you want to do, right? Okay, so now I've got my acid and I've got my base. Go through each one, ask, is it able to donate protons? Is it able to accept protons? Is it able to donate protons? Is it able to accept protons? If it is able to accept protons or is able to donate protons, then you have to determine whether it's a weak conjugate acid or a weak conjugate base. Okay? If it's from a strong acid or a strong base, then you're going to have a very weak and neutral compound, like sodium was from sodium hydroxide. And it did nothing to turn the solution basic, right? So, or acidic, it didn't do anything, right? Neutral. So the NO3 was neutral from nitric acid, and so was the chloride from hydrochloric acid, completely neutral, right? Okay, then you're going to go to the base. You're going to do the same thing. You're going to summarize, and if it's neutral and neutral, you have to explain that the Cl minus is neutral due to the fact that it's from a strong acid. If it's neutral and neutral, then your solution will be neutral. If it's acidic and neutral or basic and neutral, then it will either be acidic or basic. And then lastly, which is possible on a free response, although it looks like a huge amount of work, if you were doing it as a free response, it might not take you so long, and they might say, 1 point is given for finding the KB. You see what I'm saying? So they would break it up. All right? So in this case, you would need to find, in fact, they would absolutely break this up. You would need to find the KB of the methylamine and then the KB of the NO2. Now, how they would do this is you would find these first, and then they would say, so much of this compound is put in solution, will the solution be acidic or basic? Because you've already found everything. So that's what they would do. Okay? I gave you a very few problems tonight, like maybe 7, but I want you to do the chart, okay?